recording here. All right, so where we left off on Wednesday was we looked at the idea of a laser, and we determined that in order to get stimulated emission to happen at a rate where we can use it to amplify light, what we need to do is create this thing called population inversion, meaning we need two energy levels where most of your atoms or molecules are in the higher energy level. And if that's the case, then we could send photons through the system, perturb the system, and cause them to cause all the atoms and molecules to lose their energy and multiply our number of photons. The photon we send in has to be tuned to the space between the energy levels. But as long as that's the case, and usually it is because we use a photon that was emitted by the system to begin with to start the process. So as long as we have that photon and population inversion, we can get this lasing effect, light amplification, to happen. We looked at a few different systems, and we showed that if you just have a two-level system or a two-state system that you can couple to with light, you really can't get this to work because the population inversion, delta n, the population of atoms in state 2 versus state 1. So delta n here is n1 defined as n1 minus n2, remember? So if this is positive, it means there's more atoms in the lower energy level. And thus, we determined that that's always the case, no matter how hard we hit the two-level system with our pump light source. So no matter how big I sub p, our pumped intensity, gets, we can never get enough atoms into the higher energy level to sustainably cause stimulated emission. However, if we have a 3 or 4 level system, meaning if we had some other energy levels in there that had this fast decay property, we could use that to our advantage to build up a bunch of atoms. So for instance, here for the 3-level system, we could pump states up to the 3rd level, pump atoms up to the 3rd level. They quickly decay to one of these, to an intermediate level where they like to hang out. That causes a buildup of population inversion between states 2 and state 1. So if you could hit a 3-level system with enough energy, you can get population inversion. It's even easier if you have a 4th state below the bottom state of your lasing system. That allows for all of the atoms in state 1 here to immediately decay down to the ground state. That ensures that you always have 0 population in your lower energy level you use for lasing. So if you have a 4-level system or a material that has 4 energy levels with these properties, and you can generate photons that are tuned to these, lasing is quote unquote easy. So there's a few things here. The only other mathematical thing I wanted to find today is this quantity called the saturation intensity. So that's a constant of the material. If you remember, it was given by the constants in the differential equation, the Einstein coefficients for, so it's a absorption rate divided by rate of stimulated emission, A divided by B. We can write this out in terms of some fundamental constants. So that's the only real mathematical thing I'm going to do today. And then we're going to talk about applications. So this saturation intensity, basically, we'll talk about what it means in a second, but it's this, the relaxation rate for an excited state divided by the, what we call the absorption cross-section, how likely it is to, the system is to absorb a photon. So here you might consider thinking this rate 1 over tau. Tau would be the lifetime of, in this case, state 2, how long atoms on average like to hang out there before they decay down to a lower state. So that's kind of what A would represent. B is a measure of the probability of absorbing a photon, go from 0 to 3, more or less. So the saturation intensity can be written as this ratio. So the frequency of the pumped photon divided by this quantity, your relaxation rate or your excited state lifetime, tau, and the absorption cross-section, which measures how likely you are to absorb a photon. Those are both experimental parameters that you need to get from just doing measurements. But that's kind of just to give you some idea of what this looks like for a laser in the visible or near infrared. H bar omega is about 10 to the minus 19 joules for visible light frequencies or near infrared. For most molecules, and especially for molecules or in systems we use for lasing, tau can change. For most molecules, it's like in the picosecond to tens of nanoseconds range. So 10 to the minus 12 to 10 to the minus 8. For a system that's really good for lasing, we really want a state that has a long lifetime, where the molecules really like to hang out in that excited state number 2. So that means tau is bigger. Instead of going from picosecond to nanosecond range, for our laser molecules, we're really looking for systems that have energy level lifetimes of around 10 to the minus 9, so nanoseconds to milliseconds here, 10 to the minus 9 to 10 to the minus 3, and orders of magnitude bigger. So we can't just use any material with any energy level. We have to kind of really search around, but if you look, those things are out there. The absorption cross-section, again, is a weird quantity as units of area, but it's this measure of how likely you are to absorb a photon. The bigger this number is, the more likely you are to absorb a photon. You could kind of think of it effectively like a measure of how big the molecule is from the photon's point of view. The bigger the absorption cross-section sigma, the more likely it is that photon to be absorbed. So it's like, this is like an effective target area for the molecules in your system, if you want to think about it that way in kind of an abstract sense. So that's the one I think. The other quantities are kind of easier to see. So if you see what they mean. Overall, what this means is that in somewhere, depending on for our laser molecules, the saturation intensity goes from like 1 to 10 to the 13 watts per square centimeter, which this quantity plays a key role in lasers. So what it kind of really means is that when the intensity of the light inside the laser, or when the intensity of your pump is below this quantity. So if you remember, our laser has this outside pump light source that you're hitting it with to throw energy in. So below that, the material really, really likes to absorb the energy. As your pump intensity gets bigger than this, the medium becomes progressively less absorbing. So it's more or less a measure of how much your lasing material likes to absorb energy. So more or less, and this provides a measure, this is why it appears in all the population inversion formulas. Once you cross this limit, if you get pump intensities that are higher than the saturation intensity, that's when you start hitting population inversion. When you kind of put as many molecules up into the higher energy levels as possible, you stop absorbing as much energy. So this provides like a physical limit for what intensity you need to cause population inversion. So it's a ballpark estimate of that. Kind of physically, that's what this relates to. So let's take a look at what some actual systems look like. So the original laser was or at least visible laser was a ruby laser, where we used a ruby crystal with a voltage applied as our lasing medium. You could pump it with external light as well. So basically what happens here is that in the ruby crystal, you have some ground state, and your external pump source, whether it be whether it be electric or a light source of some form. So here in the original laser, it was a flash bulb pump. So you can see here in the figure, this part here is the holder for the ruby lasing material. You can see the crystal here. And I actually have one of these like just sitting around in my research lab that I inherited. I would have showed you this in person if we were able to be on campus. So this is the ruby crystal that we use for lasing. This kind of coil here is a flash bulb that fits around the crystal, and that provides the initial pump light source. So this is the energy source that provides our initial population inversion. And then after that point, some electron in an atom in the ruby will give off its energy, give off a photon in spontaneous emission, which will then be progressively amplified via stimulated emission. So the way this works here, you'll see you effectively have a 3-level system here. So that initial pump light source pumps with higher frequencies, and it pumps up to these like higher energy level states, kind of corresponding to the D and F orbitals in the ruby crystal. And then they quickly give off that energy as heat in the ruby and fall down to lower, kind of more stable levels and just hang out there. And then eventually the what we call the laser transition, the photon given off going from here, from this metastable state to the ground state, is the color that then we progressively amplify and lase. And for a ruby laser, that's red, and it's around 694.3 nanometers. So the original laser here, at the time, people knew a 4-level system was a better choice for an efficient lasing medium, but the limitation here was finding the materials to get this to work. As you can see kind of the size scale here, this original ruby laser, about the size of a pen. So it doesn't have to be big. But this is kind of more, a little bit slightly less cartoony picture of what the energy level systems would look like for this type of system. And to get the energy levels in the system to kind of have the right configuration, you have to play a lot of tricks with the materials you're using. So there are a lot of different ways to do this. So for instance, one thing you could do is use solid state lasers. So materials, this would be our ruby example, would be an example of this, where you combine different alloys and compounds of materials to get the energy levels to be at the right place. This is easier to do if you have numerical software that can simulate complex energy band diagrams for materials. So Ruby fits into the solid state category. The common one that's used these days has a lot of applications is the neodymium yttrium aluminum garnet, which is called the ND-YAG by those in the know. And it's an infrared laser at 1064, but there's some, you can also use some nonlinear optical properties that we haven't talked about really yet in this course, and probably won't have time to, but you could change that frequency. You could do what's called frequency doubling to produce a light at 532 nanometers. So this is one of the common ways to get combining this ND-YAG laser with a frequency doubling crystal are some of the common ways to get a very high power green laser beam. Other much cheaper ways to produce lasers, and these are the lasers you most likely have seen in your daily lives or work with, are semiconductor lasers, where if you've taken electronics, you know that semiconductors are structures that have what's called a band gap, meaning a collection of very closely spaced energy levels, followed by a gap in allowed energy, followed by more energy levels, all closely spaced. And jumping between those gaps, that gap in energy levels is the way to create a lasing transition in those materials. So the lasers in laser printers or the laser readers in CD or DVD players are based on this concept. Sometimes you need lasers that can laze over a wide band of frequencies and wavelengths. And this is true if you want to make a pulsed laser. This can now be done with solid state lasers and semiconductor lasers, but before that technology was really well developed, using organic dyes that were kind of built to have complex energy level diagrams was the way that was worked. The usefulness of these things are that they are tunable over a broad range of wavelengths. You can, by setting up the system correctly, you can pick the wavelength you want to laze at. However, the problem is it's hard to chemically manufacture these dyes. They decay and decompose very quickly, and they're almost all 100% very carcinogenic. So they are not used now because other options have less of a chance of causing cancer to the user. The lasers we were using in lab when we were doing experiments were helium neon lasers. So mixtures of gases is another way to get the correct energy level diagrams and separations. And I'll show you this on the next few slides. So for instance, the mixture of helium and neon provides a good way to some of the energy levels of one of those gases play the role of our fast decay, which gives energy to electrons in the other gas and pushes them up into a more metastable state. So you can get this type of 2 or 3 level system by combining different mixtures of gases or compounds. Sometimes you could use individual gases. So for instance, CO2 lasers, which are the type of lasers that are used, for instance, in the laser cutters at the makerspace. They are far infrared lasers. They emit light at 10.6 microns in wavelength. Those are based just off CO2 gas. If you want to laze in the UV, argon lasers are a good option for that. It all depends on where the energy levels fall and the difference between those energy levels and whether you can get this system where you have fast decay into a very slow decay energy level. This last one we're not going to talk about much, but reactive gases such as chlorine or fluorine, you can mix them with other inert gases and apply a voltage and create something that is like a temporary molecule, which chemists call a dimer. And these are ways you can excite them. They can make lasers in the UV. So they're called excimer lasers, short for excited, and dimer. And pronounced excimer. So let's go through and look at some of these different types of devices. So as I showed you before, the ruby laser, just a different view of it. This was the first visible laser invented in 1960. However, it's called the first laser, but it wasn't the first application of stimulated emission. So the idea of a laser was invented before this, and it was first done with microwaves. And at the time, that was called a maser, short for microwave amplification by stimulated emission of radiation. But the first visible light laser was the ruby laser, with this 3-level structure where the higher order D and F orbitals in the ruby relax to a lower energy state right before the above the ground state that allowed us to laze at 694.3. Since it's a 3-level system, it's not very efficient. You really need to hit it with a lot of energy, but you can make it work. For instance, a dye laser, most of the dye lasers that are used, those are 4-level systems. So this is kind of the reason they were popular for a while until we realized they caused cancer, because the complex organic dyes have lots and lots of energy levels. So it was easy to find 4-level systems there. And depending on how you set up the mirrors, unfortunately, we're not going to be able to get into the in-depth detail of laser cavity design this semester. But depending on the curvature of the mirrors in the cavity and the spacing between them, you can induce the dye to laze over different wavelengths. So these dyes, given the amount of energy levels they have, they're tunable over wavelength ranges of 100 nanometers. We could also now do this, it's more common to do this now with solid state lasers, in particular for near infrared and kind of red light tunable lasers. Sapphire crystals with titanium impurities are kind of what's used now. So for instance, the energy levels here for the dyes kind of look like this, and this is the reason why they could lays over all these different frequencies. Unlike a gas that just has these equally spaced energy levels, organic dyes that are in a liquid have all these very closely spaced energy levels. And it's possible to induce lasing over between, there are multiple different pairs of energy levels that we could use to induce our lasing transition. So this is fundamentally why dyes are so tunable. In fact, it's often like they're very easy to get lasing. The hard part in using them is getting them to laze in one direction. If you hit them with energy, you can kind of get multiple beams going out in different directions. As for what this looks like, the type of wavelength ranges over which you can get a dye to laze, depending on the different dyes you use, the different letters here are different abbreviations for different types of organic dyes. So for a long time, you could see kind of power output for lasing at one frequency versus wavelength. So all of the different dyes that were invented over the course of laser history have allowed us to get lasing both down here in the UV at 300 microns, but at some point there was a dye, an organic dye invented for the sole purpose of lasing at all these different frequencies in across the visible and into the near infrared. So this covers the entire visible spectrum and then some. This is why for the longest time, until we found them to be health hazards, organic dyes were very popular in building lasers, especially for research purposes. If you needed a specific color or a specific a laser to work at a specific frequency or over many frequencies at once, this is why dyes were so useful. Now going to the laser we use in lab. Here is kind of like a picture of what this looks like. So those lasers in lab are small helium neon tubes. And so what this means is that there's a vacuum tube inside the laser that is pumped out and filled with a very low density mixture of helium and neon gas. And together, these form a 4-level system. So basically the way this works is that you apply a high voltage to the gas tube, somewhere in the range of 1500 to 2000 volts. And what that does, that voltage excites the helium atoms. So it takes electrons in the helium atoms from the ground state up to the 1s orbital, up to the higher like 1 or 2s orbitals. Those helium states, the notation here is kind of, I'm not sure why the 3s is down here to check the source of the figure, but we excite the helium electrons up to these higher energy levels. That excites the entire helium atom and the gas itself, gives it energy, which kind of collides then with the neon atoms and transfers energy. The then excited neon atom holds that energy for a while and eventually decays to, the electrons in the neon atom eventually decay to lower energy levels. Where we were using it in lab and where helium neon gas is used mostly is for one particular transition. And that's this one. For red light at 633, or that's actually rounded, so 632.8 nanometers. So helium gas is excited, transfers that energy to the neon gas, which is stored as an electron in a 5s orbital state, and then stimulated emission, if it's hit with a 633 nanometer photon, it will induce a transition down to the 3p orbitals and give off another 633 nanometer photon. Most helium neon lasers that are used are built with this purpose in mind. So here in the lower part of the screen, you could see a smaller, or you could see kind of a schematic of what this would look like. So this clear area here is our helium neon gas tube, and the voltage is applied across the end of the tube. So you can see the power supply here, and then there's like one end of the voltage put here and here on either end of the tube. The excited gas is inside and eventually gives off a 633 nanometer photon, which is then bounced and focused with curved mirrors back through the tube and is then selectively amplified through stimulated emission. You'll notice that the windows on the edges of the tube are at an angle. And that's to make use of the property of Brewster's angle that we learned earlier in the semester. We want to get as much energy out of this laser as possible, so we want to minimize reflections from those windows. So the ends of this tube are cut and put at an angle such that for the polarization that the laser puts out, there is zero reflection from those surfaces. All of the light from that mirror goes through the tube and none or very little reflects from the surface. So there's a lot of different things we learned about in optics going on here. You may have the questions like, well, what do you have to change to, instead of getting the helium neon gas to laze at 633 nanometers, what do you have to change to get like that yellow line, or to laze at 543 or maybe 152 nanometers in the ultraviolet? And the thing you actually have to change is the curvature of the mirrors. Depending on this curvature, the focus inside the crystal will be different, or inside the, not the crystal, but the gas tube will be different, which will change the probability over which which transition is most likely to be selectively amplified. And that's something you could predict with a lot of theory, and there's some ray matrix optics and ray matrices that go into it, though it's not something we're going to really have time to get into for this class, and it's kind of especially hard to teach online. But the physics there is that it's the optical ray matrices of these curved mirrors that determine which of these transitions is most likely to amplify light and laze. And when helium neon lasers are most efficient and best for the 633 nanometer lasing light, but you can use other mirrors to get helium neon gas to laze at these other frequencies as well. The CO2 laser is like very similar. So it's kind of, in CO2 lasers, basically they are more or less air lasers, in that they're mixtures of nitrogen and CO2. It's, you know, what's in the air around us. Obviously there's oxygen in the air around us too, but you know what I mean. So what we do is pump energy into the nitrogen, which then through collisions excites the CO2 and then causes lasing over a whole bunch of different frequencies. The amount of energy you have to throw in is quite high, and that's true for all lasers, but the CO2 laser has the gets the award for being the most efficient laser ever developed, and that's about 30%, meaning the intensity you get out of the laser is about 30% of, or the energy that goes out of the laser in the beam is about 30% of the energy you need to throw in to get the process to start to begin with. So that being said, the benefits of having a confined beam of light in the laboratory are worth the efficiency loss there. CO2 lasers are also one of the lasers that we know to exist in nature without having to engineer it. In particular, the atmosphere of Mars has been shown to effectively act like a laser, which is really, really strange. But the way we know this is that we could look at emitted light from the surface of Mars. And what we see is a very clear and well-defined peak at a very narrow frequency. And the theory of why this is happening is that this peak is right, by the way, at a common laser transition peak for carbon dioxide, is that the Martian atmosphere has a lot of carbon dioxide and it's very thin. So the atmosphere is thin, sunlight is dim, but there's very little loss. So what happens is that the surface of Mars acts like one of our mirrors. It acts like the high reflector, and the edge, if you will, of the atmosphere of Mars acts like the output coupler, the partially reflecting mirror. So because the atmosphere is thin and the loss in the atmosphere is low, the gain is high, and it can and we have a really long path through the atmosphere. So overall, you can get a lot of stimulated emission as sunlight transitions from the top of the atmosphere down to the ground and back out. So it's pretty cool effect. And that lasers, before I found this result, which was last time I thought I taught this course, I didn't know about this result. And I'd always thought that a laser was one of these things that really never existed in nature, but apparently nature still beat us to it. So you can see lasers, you can see that Mars can act as a laser. There's another example from astronomy as well. And that's this unstable star called Eta Carinae. And so the two lobes you see expanding are the star is throwing off its atmosphere. And if you look at light, astronomers look at light emission from this star, and the x-axis here is wavelength in angstroms. And they see these two very sharply defined peaks instead of like a broad peak of light being emitted. And they've determined that this is due to lasing of atomic iron. So there's actually iron that has been in kind of gaseous form that has enough energy that light from the star is selectively causing lasing at these frequencies. So the way we know that lasing is happening is that in most cases, laser emission is a very narrow bandwidth. So it's not one broad peak of many wavelengths, it's a lot of intensity at a very narrow wavelength, which is what we see here. So another cool example of where you see this phenomenon in nature. Krypton ion lasers are some of the lasers that are used in lab to be very tunable. So so krypton ions can be used to laser over a whole bunch of wavelengths, though the power you get out of them varies considerably. For instance, you could see their krypton ion lasers are probably best, or you could get the most power out of them down here in red. But that being said, they will work in other ranges as well, depending on which of the transitions you select for. I'll kind of finish here with the diode lasers. So if you guys, some of you have taken electronics, some of you haven't, but for those of you that haven't, don't worry too much about it. But one thing, diode lasers are based essentially on semiconductors and stacks of semiconductors, where one semiconductor is more negative charges. We call that the N region. One semiconductor is essentially missing electrons, so it has a net positive charge. That's called the P region, or the positively doped region. This creates an energy level difference between one side and the other. And when you run a current through this diode, in electronics, the usefulness of this is that it's much easier to run current one direction through this stack of semiconductors than the other. So it acts like a one-way street for current. As far as lasers are concerned, the current that runs through this structure has to give off, the electrons or the charge carriers in that current have to give off energy as they do so. So in some ways, you can consider, this is also how we make, for instance, a photodetector or a photodiode or a solar cell. In that if we put a negative bias here, we prevent current flow. And then the only way you can get current to flow is to have, for instance, light come in, be absorbed by the electrons and give them a lot of energy, which would then allow current to flow and act kind of like an current source. However, What we want to do is actually the reverse. So what we do is apply a positive voltage, which then drives current through the material in the way it's allowed. And this is kind of a schematic of what these structures look like. And as the current flows through these structures, they give off their energy as either light or heat. And a laser diode, for instance, an LED, most of the energy is given off as light. So if you have an LED laser, or for instance, like a laser pointer that you might use, those are laser diodes as described like this. Their other benefit is that they allow us to develop and produce very, very small compact lasers. And they also allow us to pump the energy completely electronically. You don't need a flash bulb or a really high voltage source. You just need a small voltage source to run a current through the diode. So they kind of took lasers from being these laboratory devices to being these things you see every day. And these are the ones that you're probably most familiar with. So this is what you find in laser printers and in CD and DVD writing and reading devices. So any laser that you have that is compact, small, part of a larger electronic device, those are diode lasers. As a last thing here, I'm going to just kind of finish with the idea that, of course, as long as you have materials out there with lots of energy levels, and some of them are long-lived energy levels, metastable states. If you get a material, chances are there's some state in there that if you hit it with enough energy, atoms and molecules are going to build up in that energy level, and eventually you'll get population inversion, which has led to this idea that if you hit anything hard enough with enough energy, it'll laze. And if you add a couple mirrors on one side of this material and another, you can get the device to laze. So when lasers were first being developed, it was a big rush in the field to try to see if you could get different things to produce a laser beam. And this, the funniest version here is probably from Art Shallow, who is the co-inventor of the first ruby laser. He tried to make Jello laze. So he tried to use Jello to see if he could get any type of laser out of it. He didn't. He ate the Jello. It didn't work. But the attempt exists as a reminder of why we all do science, I think. Art Shallow, just as a last note here for our kind of application lecture for the week, is that Art Shallow was quoted as saying that if he had emphasized the oscillation part of a laser rather than the amplification part, that a laser would be today known as a loser. But he didn't, so we have lasers instead of losers. So that's, when we come back on Monday, I'm going to talk, I like to finish this course with a little bit of kind of what my research field does with lasers. So you can expect, I'm going to give one problem related to lasers on this material, and I'll get that to you early next week. But other than that, the remainder 2 lectures, I want to talk to you guys, teach you guys a bit about what people in my research do, which is about making lasers to produce short pulses of light. So we'll finish here for the week on this note of the laser potentially being the loser. Have a good weekend, and we'll get back to it on Monday with pulsed lasers and what we call ultra-fast optics. As a reminder, remember the problems on diffraction are due today or this weekend. If you need extra time, that's okay. If you want, I'll hang out and answer some questions. If you have any questions on the homework, I could hang out for a bit. But we're done for the week, so thank you. Have a good weekend.